lesson, we are given this DNA sequence in vivo and told that a 5 amino acid long protein is formed. In order to find which DNA strand will be the coding strand for the transcription and translation of this protein, we first need to find the nucleotides that will be transcribed and then translated into start and stop codons. Looking at the first strand, the top strand, we can see that we have an ATG, but this does not give us 5 amino acids, so this could not be the functional protein. So if we look along the second one, we do have a start codon here. Now if we look down the line, 1, 2, 3, 4, plus 5, we do have a stop codon here. That being said, we know that this strand here is going to be our coding strand. Transcribing this coding strand provides us with the mRNA strand, also going in the 5' to 3' direction. As you can see here, the transcribed mRNA sequence then encodes and is translated into the corresponding amino acid. I would like to make the comparison of going throughout our day and eating meals. So the methionine amino acid signaling the start of our day can be represented by an alarm clock. The next amino acid can be represented by our breakfast, the next amino acid being our lunch, the next one being a snack before dinner, and the next one being dinner. The stop codon signifying it's time to go to bed so we can start the process over again. The first single nucleic acid point mutation in the DNA sequence we will look at is the transversion of a G to a C at the end of this third amino acid, which will then be transcribed, which will then change this amino acid to serine. While the protein still contains 5 amino acids, the transversion of this G to a C changes the amino acid completely, now encoding for serine. This can make the protein non-functional. While it still does contain 5 amino acids, it does not contain the right amino acid for the function. That being said, our meal representation, we can see that this will no longer encode for the normal lunch that we were looking for. Instead, it encodes for the lunch that we no longer like. This ruins our whole day and causes us to become non-functional. Because this transversion of a G to a C causes the amino acid to change, this is called a missense point mutation. The next point mutation we will be looking at involves the transversion of this A to a T, which then translates into a stop codon. This transversion to a stop codon is a nonsense point mutation. This causes the amino acid sequence to not become fully translated, aka we leave dinner out, which will not encode for the functional protein we are looking for. Just as going to bed without dinner will leave us non-functional. The next point mutation we will be looking at is the transition of this nucleotide C to a T, which then transcribes into a U, which then translates into the same amino acid in the original product. So the protein remains functional. Finish the sequence and create a functional protein, just as we are able to create a functional day. This type of point mutation is called a silent mutation because there is no overall observable change in protein function. The last point mutation is the transition of this T to a C, which translates into another amino acid and not the stop codon. We are no longer stopping at 5 amino acids. We will continue on down the chain until we reach another stop codon. We will just continue to keep having meals and go without sleep. So in that, we may very likely have a non-functional protein. This is considered a read-through point mutation.